Hello, I'm Senna, and alongside Crystal, Reynold, Caitlin, and Wai, we are Team Infection Prevention in the RICE 360 Internship Program. We have been tasked with reiterating two devices that will help to mitigate the spread of infection to address COVID-19 in Malawi. Today, I will be presenting on the problem context, device material, design criteria, problem decomposition, brainstorms and stakeholder feedback, as well as our final recommendations for the walk-through decontamination unit. This device is essentially a tunnel disinfectant system that allows users who walk by to be sanitized. We have been tasked with reiterating this decontamination unit that would help to disinfect areas of the body that are not traditionally reached via normal hand washing. This unit is to be used in public spaces that experience high levels of human traffic, such as markets and banking centers. The device materials include an ultrasonic sensor, an outer plastic cover, a metal frame, a storage container, a disinfectant pump, a control system, as well as a misting system that includes nozzles and pipes that allow the movement of disinfectant. The most essential areas of concern for our device were formulated in our design criteria. The chemical safety, both of the environment and toxicity that chemicals may provide to users, is an important consideration. Ease of use, particularly for first-time users and those who will be in charge of maintenance, is another critical component. The efficacy of the device, measured in terms of the viral load, will display how successful our device is in mitigating infection. Durability is another key area, measured as the number of uses prior to maintenance. The materials that the device uses should be as accessible as possible, ideally locally sourced. Finally, the accuracy of the device is important, both in terms of the accuracy of the chemical disinfectant to be dispensed and reach target areas of the body, as well as the range and sensitivity of the device sensor. To further enhance our understanding of the device and its problem context, we deconstructed the function of our device for its users and the device system. We envision primarily two kinds of users of our device: public civilians and lab or hospital personnel. Users will walk up to the device, get instructions, walk through the unit, exit it, and dry off. They may be concerned with the design aesthetic, and ultimately, they hope to move past it to reach their final destination. In terms of the system, a person is sensed by the ultrasonic sensor. This then activates the control system, which in turn activates the water pump. The water pump pumps disinfectant from the reservoir tank to the tubing, where the disinfectant is then aerosolized and dispensed onto users. The pump shuts off after 10 seconds. We considered three main areas for our brainstorm device iterations. We looked at various drainage systems, including a grading system that collects disinfectant into a port. We also considered different sensing systems, such as a pressure plate system that would require a user to stop prior to entering the device. Finally, we looked at various ways to enhance the design aesthetic through having different tunnel shapes, such as circular arches, and differing lengths for the tunnel. We received a lot of great feedback and insight from our various stakeholders. Our stakeholders provided feedback that the use of our device for people without PPE may not be efficacious and may indeed be toxic. We also heard concerns about how to best ensure the proper use of our device. Our device received a lot of positive support from hospital and lab affiliates. In addition, the tunnel shape and design aesthetic of the device received quite a few comments and suggestions. Finally, we received input on the activation mechanism of the device and the various pros and cons of automated and mechanical systems. After synthesizing our brainstormed ideas and stakeholder feedback, plus the various lessons we learned from our workshops and mentors, we have the following final ideas and recommendations for the device. First, we hope to enhance the mobility of the device. For users with disabilities, and to better mitigate potential crowding, we recommend the implementation of a simple ramp to our device. This will also enable a drainage system to be placed underneath the device. To ensure that the device can be easily transported between different areas, we also recommend the addition of wheels with a lock mechanism. To address concerns with disinfectant runoff, we recommend a drainage system. This drainage system might include a metal grading system that will lie on the bottom of the device. Over top this, we recommend the placement of a rubber mat that will help provide grip and reduce the risk of slip. Underneath this grading system, we will place an angled plastic tray that has a central hole to allow for the disinfectant to pass underneath. The disinfectant will pass underneath this plastic tray into a funnel that will then connect it with a hole at the top of a collection container. So overall, the disinfectant will pass through a grading system, move over the angled plastic tray, and pass through the funnel to be collected into a container. To increase the ease of use of the device, we first recommend that a traffic monitor be stationed near the device so that they may ensure social distancing is adhered to, instruct on how to properly use the device, and address potential concerns that users may hold. In addition, they may distribute masks and paper cloths for drying when possible. Second, we recommend that simple graphic instructions for use should be displayed near the device, such as these examples. These should be clear, easy to understand visuals that show the positions that users should be in and for how long. Finally, we also recommend the use of a clear plastic cover on the outside of the device so that people can see how prior users move through the decontamination unit and mitigate some concerns that users may hold of the device. The use of a chemical disinfectant is critical for the current efficacy of the device. Sodium hypochlorite or hydrogen peroxide are widely recommended for use in COVID-19 by leading public health authorities. However, there are many potential health drawbacks this might present. There may be skin irritation from the aerosolized disinfectants. In addition, there are mixed scientific reports on the efficacy of decontamination chambers in preventing infection spread. This leads us to recommend that the device ideally be used in clinical settings. If the device is to be used in public spaces, face shields and masks, as well as drying sheets, should be provided to users. Ultimately, to ensure this endeavor is sustainable beyond COVID-19, we recommend the device be integrated into hospital and lab settings after. While there is a concern from medical professionals on the safety of the device without PPE and a concern for its efficacy on people in high traffic spaces, there is a keen interest from medical professionals that we talk to. The already present lab suit-ups and PPE that many personnel use and the public health knowledge that they possess will likely integrate well with the device. Finally, we believe that it is critical for the device to be thoroughly tested prior to widespread use. A testing plan should encompass all kinds of people, such as mothers walking through with children, people wearing hats, users in wheelchairs, people walking through with their phones, and many other scenarios. The viral load of people after using the device should also be assessed through a swab test. The coverage of the disinfectant, and particularly its ability to avoid vulnerable areas such as the face, should be assessed. Durability is a critical component to ensure the sustainability of the device, particularly in testing the chemical corrosiveness and the device's ability to withstand heavy traffic. Market research should also inform the future design decisions of this device. Researchers should observe and survey how people interact with the device and gather feedback from the people who maintain the device. Thank you to everyone in the Rice 360 education team, our faculty mentors, the wonderful TAs, workshop leaders, stakeholders, donors, and everyone who made this possible. Thank you for tuning in.